Hello everyone, thank you for joining us today for this new webinar. Today, Youn Vitry and Adrien Devant from Sequoia Technology and Adam Median from Fluigent will be presenting Double Emulsion Made Easy, a reliable device. Just a few notes before we get started. If you have any questions during the presentation, please use the chat panel available from the top of the screen. Our team will answer them right away or we'll bring them up during the question session. A recorded version of this webinar will be available from tomorrow, and the presentation will be available for you to download from the right panel. This webinar uses video techniques and might create some instability. Please let us know if you see any problem with them. It's now time to start. Adam, I give you the lead.
Okay, thank you, Bashir. So hello everyone, we're happy to welcome you on this webinar. First of all, I would like to introduce myself briefly. So my name is Adam Median. I'm working as project manager at Fluigent. And today, together with my colleague Youn and Adrien, we are going to discuss about double emulsion and how we can produce double emulsion with in an easy way, a robust way. So we have developed, Sequoia have developed a technology called the Redrop to make this double emulsion, and we have worked in collaboration together to highlight and to develop this project. I hope you can see the screen. Okay. We need to slide. Sorry. I think you cannot see the screen and the slide. So we are going to fix it. Just a few minutes, please. Perfect. Here it is. Okay. Control. No. Sorry for that. There is no. Okay. No, don't like this. Okay, so let's do this like this. Sorry for the delay, it's a technical issue. Okay, so let's start. So first of all, I will briefly introduce the two companies. So on one side we have Fluigent. So Fluigent, we are experts in flow control and fluid handling solutions. So we are a French company founded in 2006. And the goal of Fluigent is to provide instrumentation and product for microfluidic application. So this project can go from pressure-based flow controller to have a really stable flow into microchannels devices. And it can go from this pressure flow controller to flow sensor and also to valve that you can automate to make different, let's say, more difficult experiments such as sequential injection and in various areas. So on the other side, we have Sequoia Technologies. Sequoia is a Belgian company founded in 2019. And Sequoia provides expertise in equipment for the biopharma R&D and industry. So Sequoia can be, expertise area of Sequoia can be split in three categories, in three pilot lines. So the continuous crystallization first, then prepared evaporation, and the last one, emulsification, which is the most important topic for today because we are going to focus on that. And yeah, so the idea of the collaboration between the two companies was to bring both expertise area together to provide complete solution to customer who wants to start with microfluidics, who want to carry out many applications, such as in pharma, academic, as industries. So the idea is to provide full solution for them. So now we are going to talk about double emulsion. What is a double emulsion exactly? So a double emulsion, for those who are not familiar with that, and for those who are not aware, double emulsion can be described as an emulsion of an emulsion. These are complex systems in which the droplet of disposed phase themselves comprises even smaller disposed phase. What does it mean? Actually, It's pretty simple. It's that double emission is a droplet inside another droplet of different immiscible or partially miscible fluids. So this method has many advantages, and double emissions are an area of intense research across several areas such as industries and academics. The double emission can be found in their different forms, such as water in oil in water emulsion, oil in water in oil emulsion, hydrogen microcapsule in food, for example, where you are going to have encapsulate a reagent into an alginate shell or agarose shell. Then you're going to have polymer microcapsule for drug delivery with a biocompatible shell, such as PLGA or PLA, and various other double emission. So what are the market? Let's say double emission is a promising method with many advantages and with a high potential. So the idea of this slide is not to focus directly on the application and on the market, but just for you to have an overview of all the applications that could be made with double emission. So, for example, in cosmetics, we can make toothpaste, we can encapsulate flavor to have more controlled release of the flavor into the mouth, for example. Same for fragrance. On the other side, for food, for example, we can encapsulate into microcapsule, biomicrocapsule vitamins for slow and controlled release. We can make food supplements for taste masking, for example. On the pharma side, which is a huge market for the double emission, so we can encapsulate API, so agent pharmaceutical ingredient, into microcapsule, biocompatible microcapsule, to have a slow and controlled release of this drug over a long period of time. So this microcapsule allows to protect the API during physiological transport and allow to target specific sites or specific organ to only deliver the drug into this organ. So basically, it allows to generate and produce targeted drug delivery system. And the last one is research in biology. Emulsion has a strong advantage in this area, is to encapsulate at single cell level, so single cell, and study single cell level. So by encapsulating into droplets, you can analyze single cell. However, when you are making emulsion, you are basically making water in oil solution, and oil phase are not compatible with most of the facts which are widely used for cell sorting. So the idea here is to make a double emulsion, so water in oil in water emulsion, in order to combine both advantages of the two methods. So this is a promising method, but what are the current and most widespread methods to generate this double emulsion? So first of all, we have, which is most widespread in industry, I think, single batch method. So basically, how does it work? You have a reservoir which will be filled with two different phases, immiscible phases, for example, oil and water. And you're going to generate forces with, it could be mechanical, it could be sonication, so using a person. And you're going to mix these two solutions and generate emulsion. By doing this technique, you are able to generate emulsion. However, you will have big limitation. As you do not have any control of the flow, you are going to have a low encapsulation efficiency and a high polydispersity. So this is for the single emulsion. And for the double emulsion, actually, is almost the same. The only thing that will change is that you are going to use it 2 times. You're going to repeat it 2 times. So that means first you want to make water in oil emulsion. You're going to put oil and water into a reservoir, put forces, mechanical, for example. You're going to have an emulsion, and you're going to use this emulsion into another batch, while you're going to put another immiscible fluid and generate again forces to generate double emulsion. So as you might understood, this is a 2-step process. So which remains with a low encapsulation efficiency and with a higher polydispersity. And the thing is that using this technique, you're able to generate double emulsion. However, by using this technique, you are going to have a different population of droplets in your batch. So you're going to have droplets single emulsion, you're going to have double emulsion, and you have different size of droplets. So when you are making that kind of application, mostly in pharma, for example, you want to target one specific double emission with one specific size. So you're going to need to post-treat this batch to only count droplet size and double emission size. So on the other side, we have microfluidic technologies, which is a promising method. And we have two technologies. The first one is the capillary device, which is becoming widespread in most of the publication. So it's really widespread at research level. So the idea is to have a nozzle with two tips, one inside which will carry the core phase, one outside which will carry the shell phase. And this capillary will be aligned with another capillary in front of it to collect double emission. And both capillary will be embedded into another capillary. So this is a promising method. However, to do so, it requires knowledge and expertise. Most of the capillary devices are homemade, and they are made by using a glass capillary, by heating the capillary, then stretching, pulling, and break it, and make the alignment manually. So this is something that requires expertise and dedicated equipment. So it has a low reproducibility. On the other side, we have flow focusing, planar flow focusing. For those who are not aware, flow focusing is a cross geometry which will allow to generate single emission, basically. And the idea here for double emission is to make two flow focusing next to each other. So for those who are aware about single emission, when you are making emission with flow focusing, you are mostly limited by the physical property of the materials. What does it mean? Actually, it means that if you have a hydrophilic material, you're going to be able to make oil in water droplets easily. However, water in oil will be really difficult. And this is the same for hydrophobic material. So the idea to make double emission, the only way is to make two different coating on the same device, on the same chip. One part which will be hydrophobic and one part which will be hydrophilic. So these coating are made mostly manually. These are surface treatment, chemical treatments, which has a lifetime, so they are not robust enough. These are, as we said, planar flow focusing, and actually there is no real robust method on the market which are using both the flow focusing method for double emission. So how do we overcome all this limitation? So today we are going to present you a method which is called the red drop to generate this double emission. And Yoon from Sequoia is going to talk a little bit more about the technology and the principle of the red drop. And he will make at the end of the session a demonstration of the double emission, how does it work and how we can generate easily double emission. So Yoon, I give you the lead for this part.
Thank you, Adam, and hello, everybody. So before presenting our new device, I would like to come back to our first emulsion device. So the red drop that you can see on the top left of your screen is a stainless steel device composed of a chamber and two inserts supporting glass capillaries. You can see both glass capillaries on the picture in the middle. One is for the disperse phase, and the other is to collect the emulsion. On the injection capillary, the nozzle is fixed at the top. And due to the acceleration of the continuous phase that enters the extraction capillary, the disperse phase is squeezed and droplets are formed in dripping regime, as the picture explains it on the right. This device allows to produce water in oil and oil in water emulsion without any surfactant and without any coating on the nozzle. So the device is really versatile. And its application covers particle generation, encapsulation, and liposome nanoparticle. To produce double emulsion, we extend our current device by creating a new insert with two entries, one for the core and one for the shell. On the picture on the middle, you can see that there is an injector that is fixed at the top of both capillaries, and a double nozzle is there. This double nozzle, there is a schematic representation on the picture on the right, will guide the shell phase to surround the core phase in order that the shell phase will pinch the core phase, and then the shell phase will be pinched by the continuous phase to form the double emulsion. And you can see a picture of double emulsion formation at the bottom right on the screen. The advantage of such a device is that it does not require any coating to produce double emulsion, nor any surfactant for the production. On the left, you can see a typical experimental setup composed of 3 pressure controllers, 1 for each phase, 3 reservoirs, 3 inline filters in order to avoid to have any particles that goes inside the nozzle, and 3 valves. Well, 2 actually here, 1 for the core phase and 1 for the shell phase, which will help to prime the system. And once you are, and there is a red drop also to produce double emulsion. And once you have produced a double emulsion, you can either directly collect them, like you can see on the picture on the top, or continue with the on-chip analysis in a glass chip, for instance, like in the picture at the bottom. With the same device, you can produce water in oil in water double emulsion, for instance, water in dissolve in water, or water in mineral oil in water, as you can see at the top left of the screen. You can also produce oil in oil double emulsion, for instance, mineral oil in water in mineral oil. But you can also produce double emulsion with partially miscible fluids, like water in ethyl acetate in water. By adjusting the flow rate of core and shell phase, you can adjust the shell thickness, as you can see in the picture on the right. And all of these double emulsion were achieved with the same nozzle because there is no need of coating on the nozzle. Depending on the fluid and the flow rate, you can reach the generation of kilohertz of double emulsion, and with the size ranging from 80 to 150 micrometer. And the modular dispersity is high with a PSD below 2%. If we look at a particular example of water in dissolve in water, you can see the graph of the size of the double emulsion produced. And one the most important thing to understand is that the double emulsion size will be driven by the continuous flow rate. And so if you increase the continuous flow rate, you will decrease the double emulsion size. And now I will start with the demo, and don't hesitate to ask questions during the chat, and we will answer them afterwards. So here is the red drop double emulsion. You can see that that is the same housing as the red drop simple emulsion, and you have here the new insert with the connector for the core phase here and the shell phase here. The experimental setup is composed of 3 pressure controllers that can be operated either by computer or directly on them. Then you have a reservoir for each pressure controller. So for the continuous phase, we have water with twin 20. For the shell phase, we have desurf, and for the core phase, we have water with fluorescein. Fluorescein here is just here to help visualize the double emulsion. For each phase, you have an inline filter at 2 micrometer to avoid to have any particles inside the nozzle. Then you have a flow meter. Then you have a 4-way valve here. That is really easy and handy to start the system. 4-way valves are partly connected to the waste container here, and the other part are connected to the red drop to produce double emulsion. And so you have the core phase here and the shell phase here, and the continuous phase is at the bottom. And then you have the output capillary that is for the moment connected to a waste container. You have one light on this side to light the red drop. Then you have a 5-time magnification and a camera to see what is happening. To start the experiment, we will start by putting a flow rate on the continuous phase. a bit above 200 microliter per minute. Then we'll add flow rate on the shell phase, and we'll start at high value. Be sure that there is desurf all around the double nozzle. Of course, as the camera is taking only 10 images per second, what you see is not at the actual frequency of droplet generation. The droplet of HEF, of desurf here, are really generated at a much higher flow rate. Now that there is desurf all around the nozzle, we can decrease the flow rate of the shell and start adding flow rate on the core face. I will just adjust the focus. That's better. So we have to increase a bit the flow rate on the core face to have double emulsion generated every time. And now, by playing with both core phase and shell phase, you can manage to have a larger or thinner shell. For instance, I can decrease a bit the shell phase here, and I will decrease the shell. And now if I decrease the core phase flow rate, we will have larger shell phase. So it's as simple as this. And now that you collect double emulsion with just some glass here, and you can observe them. And I will switch to this view. So of course, it was the beginning of the experiment. Some droplets are empty. It's not because the double emulsion breaks, because really the stability of the double emulsion is solely due to the surfactant, the G surfactant. But it's because there was still some droplet of desurf alone before we do the experiment. And so if we collect new, you will have much more double emulsion. Yes, like this. And you can see here double emulsion on top of each other. And that's it. And so now, if you have any question, do not hesitate. So that's a good question. Droplets without any surfactant are not really stable. You can generate them. It's not a problem. It's not really not an issue. But they won't last long because of gravity difference and other things like that. You will have a collapse. And so the core phase, if core phase and continuous phase is both aqueous, the core phase will go outside of the shell phase and goes inside the continuous phase. So the question was how stable your droplets without surfactant are. And so the answer is that without surfactant, you can generate the droplet, but they won't last long. They will break during the transport in the exit capillary. So the question is, the solution are pushed into the capillary under a certain pressure, I suppose. What is the value of this pressure? So here, for this configuration, we are around 1 bar for the continuous phase, which is the pressure controller on the top left of the screen. We are at 700 millibar for the shell phase, which is the pressure at the top right of the screen. And for the continuous phase, we are the disperser. Sorry, for the core phase, we are at 250 millibar, which is the pressure controller at the bottom. But this pressure will depend on the capillary length and the diameter, the inner diameter of the capillary. So it will change from one device to another device. Well, not the device itself, but the experimental setup, I would say. So the next question, can you produce lower air values than 10 microns? No, at the moment with the current device, we can't do this.
However, I will myself to just add something. We can go lower than between 1 and 10. However, if you want to go at a micrometric level to make nanoparticle production, it is also possible with a single ray drop, so ray drop single emission. With a specific configuration, you can generate nanoparticle.
Question 4, can we go down to 40 micron of the core? I would say yes, but it will depend on the fluids that you use and mainly the viscosity of the shell phase. The next question, what is the material of red drop channel and can you modify the diameter of channel? How can I show it? Well, so you have glass capillary. So you have two kind of material. You have glass capillary that you can see at the exit of the capillary exit. So it's in glass, and the inner diameter is 150 micron, 50 micron in diameter, and you have the same capillary for the inlet, and on top of it you have a nozzle that we 3D print. So we can modify the diameter of either the glass capillary, so we can increase the diameter of the glass capillary, but we can also change the diameter of the nozzle. But at the moment, I wouldn't consider going lower than this diameter mainly for the nozzle, because it will be too difficult for most people to not clog it. Because there is always some fiber, some particle in the tubing that remain, and if you have too small diameter, you will clog it all the time. So that's why we prefer to limit the size of the nozzle, but we can go lower. What is the next question is, what is the mean radius value of double emulsion? The minimum radius would be that I achieved was with this configuration, 80 micrometer in diameter for the outer phase. And to reach this outer diameter, was going at 1 milliliter per minute for the continuous phase. So you have to go at really high value, and that's why I didn't include this value in the graphic, because most people won't go that high. The next question, what is the order to start with those 3 flows, if need to wait to other or start at the same time? So is as I presented before to you. So you start with the continuous phase. Then when the flow is stable, you add the shell phase. And when the shell phase is really all around the nozzle, you can start with the core phase. The next question is, what is the minimal flow rate to get stable double emulsion? So this question really depends on the fluids. With desurf and water for the continuous phase, it's around 150 microliter per minute for the continuous phase. And so for the shell phase, it's around 5 to 10 microliter per minute. But if you use other fluids like mineral oil, you can go lower to create the double emulsion. And what is your experience with cell encapsulation? Well, we didn't have done any cell encapsulation yet, because we are more focused on the technology than the application. There is too much application all around the world, so that it's not possible for us to cover everything.
And I allow myself to add something on this point. So we are developing in collaboration with Sequoia. So this technology, we are focusing on the physical aspect, let's say, of the double emission. However, we are willing to go further in the application. So if you're interested to collaborate with us, we'll be happy to work together on different applications on double emission to encapsulate cells, protein, drugs, for example. So this is something that we want to go for sure.
Yes, thank you, Adam. So the next question is, what are the ingredients of the three phase? So for the continuous phase, it's water with twin 20, which is a surfactant, but you can use other surfactant. It's really here to help stabilize the emulsion when we collect them. But the most important to stabilize the emulsion is really the surfactant in the shell phase. And here for the shell phase, it's desurf, and desurf is HFE 7500 with a proprietary surfactant from Fluigent. And for the core phase, it's water with fluorescein. The fluorescein is really here to help visualize the double emulsion, but doesn't change anything in the stabilization or anything else. Next one, what is the highest frequency of droplet generation? For double emulsion, the highest frequency that I reached was around 2 kilohertz. I can go higher, but then it starts to be a bit less stable, and so I wouldn't recommend to go higher than that. The next question is, what device have you used to cut the capillaries and get the flat tip? We use a laser cutter. So the next question is, I have a question about one of the parts of your setup. What are the filter units you are using in front of the flow unit? So you are speaking about this filter. So it is inline filters that are commercialized by IDEX, Upchurch, and you can find them on VWR or Fisher Scientific. And the part is, I think, A-430 or 431. But there is other inline filter in their catalog that you can buy. And this is a PIC filter, so that it's biocompatible. If I encapsulate the cells inside the core, then sort using fax machine into tube or well plate, is it easy to break the emulsion if I want to lease the cell, for example? I think yes, but you have to use a chemical compound to break the emulsion. Maybe Adam can answer this question.
Yes, exactly. So, for example, we have worked with, we have some experience with alginate, which is a nice hydrogel for, let's say, cells and protein. And if you want to recover only the beads or only the droplet with your cells, you have to use some solutions such as perfluorooctanol solutions to break the emulsion. So yes, this is after that post-treatment that you add. It's just to add the solution.
The next question is, as mentioned, no treatment of surface was done. How do you prevent wettability of channel with the course of time? Well, as there is no surface treatment, the wettability will remain the same. And that's why also we have limitations that other techniques doesn't have. But it doesn't change. This red drop, this device, I use it for a few months now, and it still has the same performance. So for oil in water in oil, or water in oil in water, double emulsion.
Yes, and correct me if I'm wrong, Yoon, but this is mostly the geometry of this technology, because it's in two capillary, axisymmetric capillary, which are emerged into a chamber that allows to generate, let's say, a squeezing in all dimensions that prevent this problem of wettability that could appear in other microfluidic channel chips that you can maybe know. So,
yes, exactly, Adam. Actually, what you see a 2D version of the nozzle, but the nozzle is axis symmetric. So the inner part of the nozzle is kind of floating inside the shell nozzle. I hope it really answers your question. The next question is, if the nozzle becomes clogged, is it necessary to buy a new device or can it be unclogged? It depends on the type of clogging. For instance, if it's only a particle or a reverse, a chemical precipitation, we say, that is reversible, it is possible to unclog it. But if it's like, for instance, for like alginate materials that will polymerize densely, you won't be able to unclog it. But most of the time, you can unclog the device and use it again.
and something else I want to add, if something like this appear on the nozzle, for example, you don't need to buy all equipment again. So you just have to change the nozzle, and we can send you some insert with only the nozzle in the box, and you just have to replace it actually, and you can do it on your own. So,
yes, exactly. The next question, what volume of continuous phase is required to fill the dead space inside the chamber? I would say it's around 1 cubic centimeter. So, is it possible to mix the double emulsion with external forces like heating integrated with the microfluidic device? The red drop is stainless steel, so you can heat it up. It's something that we have already done in the past, but not with the double emulsion, with the simple emulsion. And if you have more specific questions, do not hesitate to contact us here at Sequoia or at Fluigent. There is one last question. How fragile are the capillaries and nozzle component? Would it be easy to break them during routine cleaning? Yes, actually, they are quite fragile. But to clean the red drop, you don't need to open it. Most of the time, I do not open the red drop, and I clean it by placing the whole red drop inside an ultrasonic bath and flushing from the continuous phase through the nozzle. I quite don't understand the next question. Can this chip be made of PDMS device? I don't think so, because you won't be able to have a perfect alignment of the glass capillaries. Can you tune the distance between nozzle and outer capillary? Yes, you can. There will be a minimal distance that is fixed in the factory, but then you can expand the distance between the nozzle and the glass capillary, because there is screw on the red drop. I will switch from off camera. Yes, here. You have screw on this side of the red drop, and you can unscrew it a bit. And if you unscrew it a bit, you will still have sealing because of the joint.
sorry, we don't see the screen.
Yes, sorry, I forgot to.
I think you are showing the red drop, right?
Yeah,
Yeah. Okay.
I will share the screen. Yes. So it's better now. So yes, on the red drop, you have here 2 screws, and you can untighten them a bit if you need to elongate the distance between the nozzle and the glass capillaries. But the tuning of the distance will be handmade, and yeah. I will show it again for the distance. Yeah, it's really so those 2 screws, and with those 2 screws you can fine tune the distance.
Okay, so if we do not have any more questions, we're going to conclude today. For just to let you know that we have other related webinar dealing with the emulsification, droplets on various applications, so drug encapsulation into biocompatible microparticles for drug delivery. We have a webinar also dedicated to the red drop, the single emulsion version of the red drop. A publication that will be published soon, and a related application. So if you want to know more about what we can make as application with the red drop, we have PLGA microparticle synthesis, alginate bead production, double emulsion also, which are available in our website, so fluigent.com. And also we are working on liposome, and that will be released really soon. So yes, if you want to have more information about that, feel free to contact us, and we will be happy to discuss with you and collaborate with us with you on various projects. Okay, so I think we do not have any question again.
Yeah, no more questions. Thank you all for joining us today. Thank you for Adam, Adrien, and Yoon for this great presentation. As a reminder, you will be able to see a replay of this webinar by tomorrow. Also, the presentation